Hey guys, welcome to Unit 11. What we're going to do in this lesson, we'll cover day one, is we're going to be graphing polynomials. We're going to determine the roots by factoring. We're going to determine end behavior and also the y-intercept. So we'll start with this first example here. And this is what we would call a third degree polynomial because that leading exponent is a cube. And what we're going to do here is we'll review some factor by grouping. We'll take a GCF out of that first group there of an x squared, and looks like we'll take out a -4 from that second group. So in doing that, we'll have an x squared here. You take that out of both, we're left with x plus 3. If we take out a -4 from this group, we're also left with an x plus 3, which is good because that needs to be the same as the first. Now what we can do is take out that x plus 3, and what's left is going to be the x squared minus 4. And from there we can factor that into x plus 2 and x minus 2. Okay, so looking at this, our roots are going to be -3 and plus or minus 2. So what does that tell us graphically? That tells us basically that our graph is going to cross the x-axis at those values. So if we want to make a quick sketch, it's going to cross at -3, it's going to cross at -2, and it's going to cross at +2. So those are the x-intercepts. Y-intercept, where does that come from? Well, if we look here and we set x equal to 0, all we're left with is a -12. So I know it must cross the y-axis down here at -12. Okay, so now what I need to do is I need to sketch a graph that goes through those 3 points and the y-intercept, but I'm not sure which way it goes. So what I want you guys to do right now is let's just throw p of x into our calculator. Okay, so I've done that here. Don't pay attention to y2. And let's say graph. All right, so what do we notice? We notice that it comes up from like the third quadrant, goes up, crosses the x at -3, crosses x at -2, intercepts at -12, and then continues up. So sketching that quickly, it's going to look like this. So now we've got this thing that's called end behavior. What that means is as x approaches infinity, what is the graph doing? As x approaches -infinity, what is the graph doing? All right, so as x approaches infinity, that means we're moving to the right. So as we move to the right, what is our graph doing? Well, it's going to continue to go up. So if it's continuing to go up, we're going to say that y approaches +infinity. Well, how about this other one, as x approaches -infinity? Well, that basically means as we move to the left. So as we move to the left, what's the graph doing? It's decreasing. So now we're going to say as x approaches -infinity, y approaches -infinity. So how do we incorporate this? Well, take a look at our second example here, and notice all I've done is I've put in this negative in front of p of x from above. Now I've already done this on the calculator, so we get an idea of what's going to happen. Let me just enable this and take a look at the graph. So you notice here we have the same x-intercepts, the same roots. The y-intercept, though, is now +12, and it looks like the end behavior has changed. So if I wanted to sketch this one real quick, I've got -3 and -2 to +12. So now what's going to happen is the graph's going to look like this. So how does that affect our end behavior? Well, as x approaches -infinity, so as we move to the left, now it looks like the graph's going up. So y is going to approach +infinity. Now as we move to the right, so as x approaches infinity, y is going to approach -infinity because the graph is decreasing. So that's called end behavior. You might hear some people refer to that as tails. We know we're talking about an odd function here, an odd degree poly, because obviously 3 is an odd number. So that determines our tails are what we call opposite. All right, so the end behavior is going to be, one of them is going to be y approaches infinity, the other one's going to be y approaches negative infinity. Okay, let's try one more. So if we notice here, f of x equals x squared minus 4 times x squared minus 9. You could probably get the roots from here. I'm a big fan of factoring it as much as I can. So this is going to be x plus 2, x minus 2. And then obviously this is going to be x plus 3, x minus 3. So I can see that my zeros right here, x is going to be plus or minus 2 or plus or minus 3. Okay, so if I wanted to make a sketch of this, so I've got a 0 at negative 3, at negative 2, at positive 2, and at positive 3. But if you notice, this is not an odd degree anymore because technically I've got 4 x's. So if you were to multiply this out, the leading term would be an x to the 4th. So this is what we would call a 4th degree polynomial, an even degree poly. So if you think of your parabola, y equals x squared, that's an even degree polynomial. And think back to the tails of a parabola, well, you can think of them as they both go up. So if I wanted to sketch this here, it would kind of look like a parabola, but it's got this weird shape to it. A 4th degree, so it's got to cross the x-axis in 4 places. So the number of roots, we're going to have 4. The end behavior, so as x approaches infinity, as x moves to the right, y approaches infinity. As x approaches negative infinity, y also approaches infinity. So it approaches infinity on both ends. That's because our tails, if you will, are in the same direction. Now this one is a little bit more challenging to get your y-intercept. There's a couple ways you could do it, but probably the easiest is to think about what you would get if you were to multiply the original factors. So if you were to multiply those out, the last term, right, it would start with an x to the 4th, but the last term would be 36, negative 4 times negative 9. So our y-intercept is going to be 36. Now what I'd like you to do is put that into your calculator and y1 and just verify that the graph in your calculator is the same as what you see here in this example. Okay, so let's summarize our end behavior. So what you see here are 2 odd functions. In particular, they're positive odd degree. All right, and I kind of like to summarize it this way. If you notice, they both kind of have a general upward flow. So the end behavior of all positive odd degree polynomials is going to be the same. As x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. Now, I want to take a second here to talk about a negative odd degree. All right, if you just think of a linear, it's kind of easy to see, general downward flow. If you think of a cubic, it's the opposite of what you see up above. So this end behavior is going to be as x approaches negative infinity, y approaches positive infinity, and as x approaches infinity, y approaches negative infinity. So basically the opposite of up above. Next, let's wrap up here. We'll summarize our end behavior of an even degree polynomial. The easiest even degree polynomial to think of for me anyway is a parabola. And we know our happy versus sad parabolas. So you can see here these are positive even degree. So I call them the tails. The tails are both going to be up. So as x approaches negative infinity, y approaches infinity. And as x approaches positive infinity, y again approaches positive infinity, because both the tails are up. All even degree polynomials will have the same y values for end behavior. Now if we think of our negative even, so you can think of your sad parabola, or if we have a quartic, 4th degree. So basically what's going to happen now is y is going to approach negative infinity. So as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y again approaches negative infinity. They'll go the same direction, both down. All right, so this will wrap up the first lesson please do the homework that's associated with this, and then feel free to contact your teacher if you have any questions.